Okay, here we're given a table representing the average hourly manufacturing pay. H represents the hourly pay in dollars and T years since 1970. Okay, we're going to create a scattergram of T comma H. Okay, so these values are kind of nasty values to deal with. We have T years since 1970, and our scattergram for T comma H, so T is the year since 1970, and H will be the hourly pay. Okay, so to create the scattergram, okay, I have this all done. Again, this is just for the sake of time, so it doesn't take 20 minutes to do the scattergram here. Okay, we think about where are we going to stick our axes? Well, T, again, is the year since 1970. The first value we're given is 1970, so that'd be a T value of 0. And then 1980 would be a T value of 10. 1990 would be a T value of 20, and so on. Okay, so it looks like we need to fit T values from 0 all the way through, well, 2010 will be a T value of 40. So those are T values that we have to fit in. H for the hourly pay. Okay, it looks like $3.24 was the lowest and increases all the way to 1862. Okay, so it looks like we started at around 0 all the way to maybe like 19 or 20. Okay, those would be values to fit in for the hourly pay. Notice there are no negative T values and there are no negative H values, which means we're going to put our axes in the bottom left again, like we did in the previous examples. Okay, so again, mine's all done. Okay, so we put our axes in the bottom left here. Okay, so the vertical axis is all the way to the left, and the horizontal axis is all the way on the bottom. The year since 1970, that is our horizontal axis for T. Okay, T years since 1970. Okay, and then when we label those, now I labeled every other tick mark as a 10 just to spread it out some. Okay, so you notice that when you notice how the points plotted here, it's spread out pretty nicely. And all the way to 40 will fit in very easily doing that. If you said every tick mark was 10, then you'd only have 4 tick marks and you'd be ending right here, which means you're wasting too much space on the graph. So here, every tick mark is 5. Okay, even though it's not going to show up when you actually plot the points, like a 1975, 1985, and so on. Okay, it does spread it out nicely. Okay, and then going up the side on the vertical axis, again, if we start at 0 and every tick mark, I just said 2 for the scale, and that fits up to 20 rather nicely. Okay, so that's a pretty good scale to use. Now, if you use a scale of say like $1.75 or $1.80 or $1.90 or something like that, it's not that that's wrong. It's just that it's going to be kind of difficult to plot the points when you actually go and plot them on the grid. Okay, but you can use any scale as long as the points fit in there nicely. Okay, so we make the scale, and again, if you need to pause the video, okay, please do that, and don't just try to catch up with me. Okay, pause the video, rewind it, do whatever you need to do, but I'm just trying to save time here on the video. Okay, so once we have those points plotted, okay, I don't ignore that I have the line graph there right now. The graph of the points without the line drawn, that is your scattergram. So if I ask you to draw a scattergram, that is it, without the line drawn in there. Now the next question says, is the data exactly linear? Now this is going to be a little different than what we had previously, because is the data linear? Well, it looks like if you were to take a ruler and try to connect any 2 points, it looks like those points will be close to a line. Okay, it looks like we could draw a line that goes through all the points. Now, we got to be careful though. We previously mentioned in order to be linear, and this is a concept we're going to build on, but to be linear, the rate of change has to be constant. Now what that means is that every 10 years, so from 1970 to 1980, 1980 to 1990, in order to be linear, the hourly pay will have to change by the same amount over each 10-year span. So a previous example we had was the profit of a company after T years. So the profit increased by $2 million every time the year went up by 1. Okay, it was exactly up $2 million every time the year went up by 1. Well, here, what it looks like is, in that first 10-year span, if we actually did find the change in the hourly pay, oops. So if we do 715 minus 324, that's a change of $3.91 in those 10 years. The next 10 years, we went from 715 to 1078. So that difference, 1078 minus 715, is $3.63. Now they're fairly close to each other, but they're not exactly the same. So these data, or these points, are not exactly linear. Okay, so even though looking at the grid, it looks like that this line is going through all the points, you have to remember that we really estimated where those points were. Okay, so when we plotted the point at in 1980, so when t is 10, we had $7.15. Okay, that is an estimate of where that point is because of the scaling. Okay, here we have 4, 6, 8. So $7.15, it is really hard to know if we landed exactly where we're supposed to on that point when we graphed it. Okay, so again, the rate of change in those first two 10-year spans changed from $3.91 to $3.63. So that is not exactly linear because we didn't go up the same dollar amount over that 10-year span. Okay, so not exactly linear. Okay, so this gets us to the idea of being approximately linear. Well, does it look like a line is pretty close to those points? If not exactly, they're pretty close. So yes, we say that this data will be approximately linear. Okay, so now we draw that linear model. And when you draw that approximate linear model, you want to draw it where that line is quote unquote close to the points. Okay, so that's the line I have drawn in here. Okay, so that is our linear model of the data. And again, it may or may not be going through at least one of the points. Okay, again, because we don't know exactly where those points are because of the scaling and the values we were given in the table are hard to plot. Okay, part E, use your linear model to predict the average hourly pay in 1985 and in 2020. Well, 1985, okay, that is a time, okay, or a year. Well, on our axes, we have t values, where t is the years since 1970. So 1985 would be a t value of 15. 2020 would be a t value of 50. So when t is 15, so 1985, t value of 15, it looks like we go up and hit the graph almost halfway up here. Okay, so we might estimate that to be about $9. Okay, so right around here, about $9, because this is 10 right here. So 8, 10, halfway up would be about 9. And then when t is 50, okay, it looks like we're just above this tick mark right here, going straight across. That'd be 22, but we're just above that. So maybe 22.25. So $22 and a quarter. If you said like $22.10, that's okay. $22.30, that's okay. But a little bit above $22, okay, because it looks like we're just above right here. Okay, so those will be our predictions for the average hourly pay in those years. Okay, next thing we look at in part F, we use our model to predict the average hourly pay in 2000. And how does this compare to the actual value? Okay, so the prediction in the year 2000, well, 2000 is 30 years since 1970. So we go to a t value of 30. And if we go straight up, okay, it looks like it's very close to the point on the grid. But again, this is going to be an important concept here, is that we don't care what the actual table says. We're using our model to predict the average hourly pay in the year 2000. So what would you guess that value is right there if you go straight across? Well, it looks like it's going to be a little bit above 14. Okay, so what I said was about $14.30. Okay, that's just from using the grid or the graph. Okay, it looks like we're right about here, straight across, be about $14.30. And again, there's going to be some variability there as far as what you could answer. Anything between like $14.10 to maybe $14.50 will be a pretty acceptable answer. Okay, and again, it's essential to understand we're estimating from the graph, we're not using the table. Now, how does that compare to the actual value? Okay, now the actual value we know in the year 2000 was $14.32. Okay, so we can see that those are very close to each other. Okay, so again, the reason I'm asking this question is I want you to understand that when it says use your model, we do not care what happened in the table. We don't care what the actual values were. We're using the line, our model, to make a prediction. Note that the actual value given in the table may not be the same as the predicted value on the model. Okay, that's very important to understand. Okay, and then in part G, use our model. So again, we're going to use our line to predict the year when the average hourly pay is $16 per hour. So $16 per hour, that's of hourly pay. We go straight across and we hit our model right here and then straight down, looks like right around here. So here's 30, 35, 40. So it looks like we're maybe at like 33 or 34. Okay, so I said 34 for mine. So that's a t-value of 34, which would be the year 2004. And then part H, discuss your model by describing some of its features. So where does it start? Does it increase, decrease, or stay constant? And how fast does it change? Okay, so where does it start? So it looks like our line starts right around maybe $3. Okay, so here's 0, 2, 4. It looks like about halfway up there. So we would say it looks like it starts at about $3. Okay, and then does it increase, decrease, or stay constant? Well, we notice how as time goes on, it looks like it gets higher. Okay, so we would say increases. And then how fast does it change? Well, how fast it changes, we already talked about how over the 10-year spans here from 1970 to 1980, we said it went up, I have the calculator here. It went up $3.91 over that 10-year span. And then from 1980 to 1990, it went up by $3.63. Okay, so it looks like how fast it changes, or so how fast does the hourly pay change? Okay, you might want to estimate maybe around maybe around $4 every 10 years. Now, if you wanted to say, well, maybe average those two together. But if you went every 10 years, okay, you might get an estimate of maybe about $4 in the change. Okay, now again, this is the concept we'll build on throughout the course. But right now, I just want you to understand that when you look at how fast does this change, it looks like in that 10-year span, it looks like it goes up right around $4. Okay, and then up another $4 about, and then to the right 10 years, up another about $4 to the right 10 years. Okay, so it looks like it increases by approximately $4 every 10 years. And again, if you said like $3.50 or $3.80 every 10 years, that's fine also. Okay, because we're just kind of getting an estimate here. Okay, you can also look at that as, instead of being $4 every 10 years, you can look at that as being 40 cents per year, or $0.4 per year. Okay, the next example deals with the altitude of a hot air balloon after T minutes as it begins to land. Okay, so after T minutes, and A is the altitude in feet, okay, so it begins its descent or begins to land. So after 0 minutes, it was 1,800 feet in the air. After 1 minute, it was 1,600 feet, and so on. So we can see that the altitude is getting lower as the time goes on. Okay, so a scattergram here. Again, the idea is, where we're going to put our axes to start with. Well, notice that there are not going to be any negative times or negative minutes, and the altitude starts at 1,800, and if it's landing, eventually it's going to hit the ground, and the ground will be 0 altitude. You're not going to have any negative altitudes. Okay, so our axes will be in the bottom left-hand side of the axes, and I'll show you here in a second because it's all done. Our t-values, we have to fit from at least 0 through 6. Our altitude, 1,800 is the highest. Now, we're going to look at 0 as being the lowest. Even though it's not in our table, we may be concerned about, well, when will it land? So we don't want to just end our values at 6 and 600 for that last point. We want to be able to fit a little bit more in. Okay, so knowing that, we're going to put our axes in the bottom left again. We have the number of minutes. Okay, so it starts at 0, 1, 2, 3, and so on. Okay, t is your variable for the number of minutes. And then going up the side is the altitude. We have to fit from 0 to 1,800, so I just use a scale of 200, okay, to fit in pretty nicely. And figuring out that scale is just a matter of sometimes trial and error, or just, I won't say guess and test, but kind of just use your judgment. Okay, obviously using a scale of 1 going up the side, or 10, as you say 10, 20, 30, 40, 50, you're never going to fit to 1,800. Okay, so you just want to kind of get good at thinking a little bit ahead and not trying to waste too much time. One thing you can do is you can count the number of tick marks that you have. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 tick marks. And you have to fit from 0 to 1,800, which is a difference of 1,800. So if you did 1,800, those are the values you need to fit in, or the range of values you need to fit in, divided by the number of tick marks, 128.57. So that would be the smallest scale you'd want to use. Now, I would never suggest using 128 as a scale or 129 as a scale, but if you use maybe 130, that would be okay. 150 would be okay. Now, I just use 200 because that fit in pretty nicely. Okay, so we label our axes. We're going to label our tick marks, plot the points. Okay, so 0, 1,800, okay, will be this point here, and then 1, 1,600 will be right here. Now notice how 2 is not in the table, so we skip over that and go to 3. So 3, 1,200 will be this point, and so on. Okay, so without this line drawn in, that is your scattergram. Okay, and then in part B, I ask you, is the data linear or approximately linear? Well, this one is exactly linear because all those points will lie exactly on a line. Okay, looking at the table, what we look at is, notice as the time goes up by 1 minute, what happens to the altitude? It goes down by 200 feet. So from 0 to 1 minute, the altitude decreased by 200 feet. Now the next values in the table from 1 to 3, that is an increase of 2 minutes. Now notice what happened with the altitude from 1,600 to 1,200, that is subtracting 400 feet. That is actually the same rate of change because negative 200 in 1 minute is the same as going negative 400 in 2 minutes. You basically went down 200 feet twice. Okay? And then from 3 to 4, so in that 1 minute, we went down 200 feet. And then from 1,000 to 600, that's going down 400 feet. But we went up 2 minutes again. So that change is still constant. Okay, that rate of change is still constant. Okay, so we draw the linear model in. Okay, so that's the green line there. Estimate when the balloon lands. Well, the balloon will land when the altitude is 0. The altitude is 0 when we get down to the 0 on the t-axis. So we look at this point right here, which it looks like is 9, 0. So after 9 minutes, it looks like the balloon will land. The 0, 1800, this point right here, that would represent the height of the balloon when it began to land. But when it actually lands is when the altitude is 0, okay, which is when the A is 0. Okay, use your model to write the ordered pair representing the altitude at 5 minutes. So after 5 minutes, it looks like we're right at this point right here, which is 800 feet. So as an ordered pair, 5, 800. Okay, and then write an equation relating the variables t and a. Check your equation using 2 different points. Okay, and again, this is not going to be an obvious concept, but we build on it throughout the course. We want to think about how do we find altitude as time goes on. So we look at starting at 1800. What do we do every time we go up 1 minute? Every time we go to the right 1 minute. So it looks like every time the minutes increase by 1, what happens to the altitude? It goes down 200 feet. So your equation to find our altitude, we start with how much? Well, we started at 1800, and then we have to take away 200 feet every minute. So in 1 minute, we would take away 200 feet. In 2 minutes, we would take away 200 feet twice. In 3 minutes, we would take away 200 feet 3 times. So we get taking away 200 feet t times. Okay, so there's the equation for your for relating the variables together. So to check that equation, again, if this equation is actually